Good morning, mathematicians. Welcome back. I have so many ideas for things I would like to talk about today, actually. Normally, I'm starved for ideas. Maybe I should make an ideas note. Um, yeah, maybe I should make an ideas note. Uh, I'll make a note. I should open up. I should really open up chat, but um, inverse Galois problem for p-adic fields. There's a paper I want to take a look at. I know New Wave Infantry wants us to look at automorphic forms. And what else was I thinking about looking at? Oh, yeah. L functions and Brauer characters. Yeah. Whole bunch of fun ideas that I want to spend time reading about. Or maybe I should be teaching myself operands live. I don't know. I don't know what the answer is. And I don't think you know what the answer is. Hello, Kostaka Kori. Hello, Locke. Welcome, welcome, welcome. Or maybe I should be teaching myself operands live. I don't know. I don't know what the answer is. And I don't think you know what the answer is. You solved the CGA bug. Nice. In the process, though, you think you've introduced a new bug. Yeah, well, welcome to writing code. Yeah, I do be like that. Yeah. So, I don't know. No, what do I want to learn? I want to read about L functions and Brauer theory. If New Wave Infantry pops back up, or uh, watches afterwards, and is like, "Hey, I wanted automorphic forms," then we'll do automorphic forms. Well, good luck. Good luck in your probability exam. Good luck in your exam. In fact, instead of good luck, I wish you good brain power. Because luck is helpful in exams, but what's better is having good brain power, having a good sleep, so that you think effectively. That's what I wish for you tomorrow. You're gonna ignore it until you have to care about it. Also, did you check out that 1 minute? I did watch that video. Yeah. Yeah. Let's see. There's some. I want to see proof of meromorphicity of L functions via Brauer induction. Yeah. Tell me, where do I read more about this? Artin L functions? Maybe here. Yeah. 1 minute is a bit long, so you skipped it. Yeah. Yeah, who has that kind of attention span anymore? I think I looked at this, but these are a set of slides. I want some notes. Analytic class number formula and L functions from Venkatesh. Maybe that's what we want. L functions, analytic continuation. Epstein. Uh-oh. This is a bad document. Is this what they meant by the Epstein files? Pages and pages of unreleased proofs about L functions. Time to learn a new thing today. You have zero knowledge about L functions. Well, the Riemann zeta function. That's an L function. Yeah, okay. Maybe we start with the shorter diagram. Oh no, it's sideways. Uh, oh, okay, we fixed it. Hooray! Oh, Ram Murti. Okay. Yeah. Hello. Sorry, I don't know how to pronounce your name. Otherwise, I would. But hello, Moon. I'll call you Moon because your profile pic. Yeah. So one L function. One L function. I'll tell you another L function. Actually, wait. No, I don't want to. I'm afraid I'll say it wrong. We'll see more L functions in a second. The celebrated conjecture of Emil Artin about the holomorphy of his non-abelian L series has inspired a vast amount of development in number theory. Langlands, of course. Notions of base change, automorphic induction converse theory. Yeah. Second method initiated by Sayre. Sayre's conjectures imply Artin's conjectures for two-dimensional complex odd representations over Q after the success of Wiles, Buzzard, Taylor proved a theorem that makes significant advance towards the A5 case. We'll refer to these papers as ST. Focus on analytic aspects. Okay. Hello, also new. Welcome, Door. Welcome, Door. Is there like a translate button? How do I... Let me... Let's go to Google Translate. When your life is an L function, yeah. Taking the L function. Analytic number theory. Oh, welcome. Oh, right, Leo. I forgot that you. I thought that. Yeah. These are Chinese characters? Yeah. You're new here doing topos theory. Oh, well, welcome. Maybe one day far in the future I'll get to sheaves via topos theory. L functions are generating functions for number theory. Yeah, that's one way to put it. Well, I don't know. It's not wrong. Yeah, Nikolai, yeah, I thought we'd discuss tomorrow. You were right. It was that time, 3 hours from that time, but I think tomorrow. Does that work for you? I hope that's I hope that works for you. There's lots to learn in number theory still. You want them to finally release the Eisenstein files? Yeah, we've been asking them for years, and yeah, but I think it should be coming up, right? They're like the Eisenstein files are mandatory public knowledge. I'm doing good. Femino. Learning Chinese? Well, not really. I learned a little bit right here. If I just memorize the string of characters, then I'll know how to write analytic number theory. Tomorrow works. Today too. Okay, cool. Yeah, let's stick with tomorrow. I may possibly be able to start sooner. I'd only be able to let you know pretty last minute, but by no means do I expect you to hold your breath for that. We can just have it at the time that we said, and then we'll if you happen to be ready earlier and you see my message, then maybe we start a little bit earlier. But yeah. Okay. Where are we here? When the inertia is trivial, which is the case for all unramified K, the conjugacy class is called the Artin symbol. In all cases, it is a well-defined conjugacy class modulo inertia, and the Artin L function is defined as this. Wait, when the inertia is trivial, yeah. But wait a second, don't we? But what do we do? What do we do? Do we just take the product over trivial inertia? Don't we got to do something for ramified primes or whatever? We usually abbreviate this as this, since chi being the trace determines phi up to equivalence. Wait, phi is just some arbitrary Galois representation of the Galois group, right? Tell chat what inertia being trivial means, because you're forgetting now, because of educating chat. I guess your knowledge set is smallest in the stream. Well, who knows? Stream isn't big, so doesn't mean a lot if your knowledge set is smallest in stream, because it could still be pretty big. You're only studying high school calculus. Well, consider this, this is your exposure to some higher level math. You take fixed points by inertia. Yes, that's true. Oh, Jose. Oh, you've rejoined us in stream. It's been so long, I feel like, since you've chimed in. I would like to, Jose, for the maybe I was thinking maybe I teach myself enough about this to give a talk in the number theory group about holomorphicity of L functions and induction on characters. I know something interesting there. Something Galois group primes. Yes, exactly. You have a proper subset of the infimum of everyone in the stream. There's something charming about those photocopy style shaky letters in such PDFs. Yeah, makes me want to have a printed out version of a photocopied version. Somehow it fits into the vaporwave aesthetic in my mind. Yeah, so actually it's a good thing Jose's here, because he'll correct me if I say something stupid. So we have an extension of let's say the rationals, and we have a prime ideal in the ring of integers of this extension, and it sits over some prime ideal, which is to say a prime number in the integers, which is to say that the ideal generated by this prime, it will split general. I mean, it may not. It may remain prime, which is to say inert, but it will be, it'll break into some product of ideals. Finite algebraic extension. Yeah. Yeah, well, I'll never watch that video, Leo, of you putting symmetric difference in F tier. I'm still mad about it. It's an 800-page Springer book from quaternion algebras. And it discusses their L and zeta functions. Voigt? Hang on a second. I'll come back to this algebraic number theory in a second, but Voigt quaternion algebras. Is this it? Whoa, baby. Look at this 800-page beast. Hell yeah. I'm liking what I'm seeing. I am liking what I'm seeing. Let's see. Let's do this table of contents here. Quadratic forms and arithmetic, modular forms and geometry, all good stuff. Quaternion algebras, involutions, quadratic forms, all good stuff. Characteristic 2. Ooh. We're getting into some nasty, nasty things in this book. Simple algebras, lattices, orders. Yeah, wow. Quaternion algebras over global fields. Wow, this is crazy. Picard group. Ooh, non-commutative Dedekind domains? Excuse me? Ooh, that sounds interesting. That sounds very interesting. Man, there's not enough hours in the day. There really isn't. There really, really, really isn't. Wow, Adelic framework. Damn, this is crazy. It just keeps going. Yeah, this book just keeps going. Wow. The 642 triangle group, huh? Damn. This is crazy. Why exactly this? Well, this is not a quotient. Oh, I see what you're asking about. Yeah. Well, because this is left cosets and these are right cosets. Right? So this means that so like this is the set of all elements where you have something like this. So we want a double coset. So sometimes you have it on left, sometimes you have it on the right, sometimes you have both. Can you tensor up to C to get a branched covering of C? What? I don't know what you mean there, Leo. If you tensored these fields, tensor over what? I mean, if you tensor these things over C, you're just going to get, like, C. There's cool Clifford algebra books you discovered recently in the bivector. There's a bivector Discord. There's an entire Discord for bivectors. That's wild. What are we up to today, Rod? Well, we're talking about some L functions and holomorphicity of L functions. I want to understand the proof of like somehow you use. I saw from like there's the formula for induction on characters. It's like basic representation theory 1 stuff. But I keep seeing it's like, oh, this was a critical thing to know for the proof of like holomorphicity of L functions. And I'm like, why? You remember my modular form series? I always quotiented the upper half plane on the left instead of the right, which tripped you out. Yeah, I mean, this is the reason. This is the reason because eventually, like this is the upper half plane, and we want to realize it as a double coset to get the connection to automorphic forms. L functions for modular forms, not quite. L functions attached to number fields. In the knowledge category of this chat, you're the object through which everyone else factors uniquely. Learning arithmetic geometry and higher topos theory. Hell yeah. Sounds based. Yes, special case of Artin's conjecture, exactly. You cast doubt on learning a proof with running chat. It is all effective. Well, maybe. Yeah. I mean, if I get more disciplined. Well, if I go back, I think I learned a fair amount during my spectral sequence series and my Galois cohomology series. And in fact, I think chat even helped. it maybe slowed down the pace of my reading, but it increased the pace of my learning because I made stupid mistakes that chat corrected me on. Anyway, so we've got this we've got this extension of number fields. And by the way, if it's Galois, then all of these e's are the same. If it's a Galois extension, and we get this nice formula where the degree of the extension becomes the product of E. Also, all the F's become the same, the F being the order of what we call the residue field. All of the F's become the same, and it turns out to be this, EFR. Or I like ERF, because then it spells ERF. Or, actually, I've never spelled it this way before, but fur. I don't know. So then, what do we do in this case? So then we have, if G is our Galois group of this extension, then G is going to act on, it's going to act on these primes. And so G will act, it'll act on the set of primes above P. So it will take a prime above P and it will send it to another prime above P. Apparently your attempt at bypassing YouTube got axed. Let me have a take two. At what? What are you trying to share? Bivector. Yeah, Locke is the master of bypasses, I would say. What if G is something else, like an old flame you haven't seen in years but recently connected with? Then you're cooked. Leo. Absolutely cooked. Yeah, so it acts on all of these primes. And then what? So then the group, what am I trying to say here? Then you take the stabilizer. Of one of these primes. You take the stabilizer of one of these primes. Say D, I'll just call, P is some random PI, doesn't matter. That will surject onto, right, because it's since it stabilizes this prime, it will give you a morphism. It'll give you a morphism of this quotient. But this quotient is isomorphic to a finite field, and sometimes we write it as like P over P. So you end up getting, or sometimes we write it F, math frac P over FP, right? So you end up getting a surjection. End up getting a surjection onto here. This is called the decomposition group. You would need to get a branch covering of C. Indeed, get a branch covering of C, but not of spec C. And branch coverings of that are boring, yeah. Spec CN? Was wondering if you get some interesting A1C branch coverings, but don't think so. Yeah, you should have been paying attention. Now you're lost in the sauce. But everything, okay, here's the point. We have the stabilizer subgroup of the Galois group. It surjects onto some Galois group of this finite extension. Then the inertia group, the inertia subgroup, is simply the kernel of this homomorphism. And so what does that tell us? Well, the order of this group, by the way, is wait, is this equal to the order of the yeah, this should the order of this group. When am I about to say something stupid? The order of this group is F. Is that true? I think the order of this group is E. Am I crazy? Am I crazy? Something like this is true. I don't remember. Where's Marcus? Where is Marcus? Yeah, let's not get it twisted here. Where's the statement I'm looking for? Frobenius. We love our Frobenius. Where's the order? I think I missed it, actually. Yeah, I think he said it already. Yeah, decomposition group, inertia group. Degrees, inertial degrees, random ramification. Aha, by Galois theory, we know that this is the same as the index here. Right. Inertia is F, and ramification is E. Right, but the inertia group, what's the order of the inertia group? Or you're saying the order of the inertia group... yeah. Moreover, both groups have order F. Whatever. The point is, some of these numbers match up. I don't remember. The decomposition group is the stabilizer of one of the overprimes, right? Because the Galois group will send a prime lying over P to another prime lying over P, and in fact, it'll do so transitively. And then what you do is you fix. You look at the stabilizer. You look at the stabilizer of one of those primes lying over P. That's what you look at, right? And think about it. It needs to stabilize the prime over P because that's why it's going to descend to a quotient of this finite field, because it preserves that ideal. So it gives you an automorphism of this finite field. The degree of the extension of the finite fields is F. So the order of inertia is E. Okay, nice. I wrote it correctly the first time. Right, and that makes sense. Right, that makes sense with the ERF formula, because the decomposition group should have order EF, and then we've got, it's a short exact sequence here. Yeah. Anyways, that's what the inertia group is. So somehow it measures the extent of your ramification. So now that we're all caught up, we can head back over to this book. And that's what we see here. So phi, in this case, is a representation of our Galois group. V is the underlying vector space. IP is the elements, is the subspace of all elements that are fixed by everything in the inertia subgroup. Yeah. Yeah. The bypass earlier, yes, yeah, I picked up on that, yeah. You're back in the present. Great. What did you miss in the few minutes you were gone? A complete explanation of algebraic number theory. So inertia trivial literally just means unramified. Yeah, it's like another way to express a lack of ramification. Trivial inertia is equivalent to being unramified. Yeah. I mean, yeah, and so if inertia was trivial, if you were unramified, then this would just be the whole space. Great. So that's our L function. Artin showed that the L functions satisfy these following properties. Oh hell yeah! Let me write this one down. Let me write this bad boy down. So, wait, what notation were we using for the fields? Oh, I don't like big K and little k. Let me do E and F for field and extension. Come on. I'm a sane person here. So LS tau of E over EH is the L function attached to the induced character. Attached to the induced character of E over F. That was badass. That was, what a cool formula. What a cool formula, I think. We have the famous Artin's conjecture. For any irreducible, non-trivial representation, we claim that this extends to an entire function of S. Open problem, by the way. Open problem alert. Holler in chat if you're ready to solve this open problem. Literally never thought of E over F as a field and extension. F for field, E for extension. Come on. What you understand of L functions is that some symbol goes in, some representation goes in, some group goes in, and something comes out. Yes. Right? I mean, what is the L function like? So, so remember that the Riemann zeta function has an Euler product. It has an oily boy, right? Given by this. L over K is acceptable, Fimnal. I'll allow it. But you can't argue with me that like E over F makes more sense. F for field, E for extension. They're alphabetically next to each other. I mean, it's perfect. It's obviously what God intended. And by God, I mean the supreme fascist that Erdős talked about. Like, what is L over K? K for, oh, maybe German. Okay, it's acceptable if K is German for field and L and extension starts with L in German, but I don't think it does. I am an oily boy. You're damn right. You're goddamn right. Right? So this looks, right? This is overall primes P. This formula looks very similar. It's overall primes P of something kind of similar looking, right? The determinant of 1 minus phi Frobenius, norm of P to the minus S, restricted to this inertia space. And guess what, by the way? Guess what? Let's take this representation. Let's just look at the trivial extension, and let's take this to be the trivial representation. So now there's no determinant. It's just a one-dimensional representation. And what are all the primes? Now they're literally prime numbers. So it becomes 1 over 1 minus, well, this doesn't do anything. It's the trivial representation. What's the norm of a prime? Well, that's just equal to P. And holy shit, we recovered the Riemann zeta function. So actually, the Riemann zeta function is just the most trivial L function for dumb little diaper babies. And number theory is about more powerful functions than the Riemann zeta function. So there you go. L'extension. K for Cooper. I see. Direct translation is body and L because of the alphabet. Yeah, so it's not, right? E over F is better because it has because of the alphabet, but also F for field and E for extension. I mean, yeah, you just can't beat it. Phi is an E-rep of the Galois group, yep. And sigma P is Frobenius over P, yeah. Yeah, can't even handle the baby. But somehow the baby is the more complicated thing, right? Like, we know some things about other L functions somehow because they have more structure. Like the reason why the baby's so hard is because there's just less structure in some sense, I guess. Yeah. So. So we have the famous Artin conjecture. In the case that it's one-dimensional, Artin proved his conjecture by establishing what is now called the Artin reciprocity law. So he proved for one-dimensional non-trivial characters that there is a Hecke character of K such that these L functions agree. This theorem is considered to be one of the masterpieces of class field theory. It embodies all the classical reciprocity laws, such as quadratic, cubic, and higher reciprocity laws. Yeah, I want to better understand that statement as well. I've seen a sketch of this proof in Dietmar's book, for example. But somehow I still haven't internalized how all the reciprocity laws are encoded. I mean, I've seen this in terms of like when you write out the L function for, say, Q adjoin the square root of P, and you end up seeing like a Legendre symbol like pop up in your L function, but still somehow I need to feel it in my gut. You know what I mean? And G's an old flame who has changed and fixed her old problems, but you still feel tension and worry about going for something more. Free therapy session for Leo. Man, you're really going through it right now, aren't you, Leo? Just don't have kids. Yeah. So in some way, LMFDB is just a list of generalizations of zeta function. Well, LMFDB is has a lot more going for it than just that. L functions generalize the zeta function, but yeah. You're about to say, show chat why that is for chat's benefit. Wait, show chat why what is for what? For what? Huh? Brauer showed that this extends to America. Yeah, maybe. What am I doing? Why am I not just looking at Brauer's original paper? It's probably because I'm scared it'll be too hard, and modern exposition will be nicer for my little brain. Yeah. Okay. Brauer's induction theorem, yes, this is what we want, states that any character of a finite group can be written as induced from nilpotent subgroups where these phi are one-dimensional and the ni are what? The ni are C, for example. Stupid photocopy got cut off. But anyways, so Brauer induction. Brauer, right? Brauer tells us what? Brauer says, Brauer didn't say. Any character is induced from nilpotence. I wonder, is there any version of this for like Lie groups or something? how you get reciprocity laws from the equality of these two functions. Yeah, maybe we'll come to an understanding of that collectively eventually. Because they're generating functions for point counting. I'll accept that for now. NI are left as an exercise, yeah. And reciprocity laws basically rules for how each prime splits. Yeah, I mean, I think there is like, if we look at this book, why are we not using Castle's Froelich? That was a good question. Why aren't we using any book that we're not using? I have no answer to this question. Like, there is, in this book, there's some computation with an L function that does basically reduce to, quadratic reciprocity to prove something about this L function. Now I don't know where it is, though. But yeah. So I guess you could view, yeah, maybe you could view it as a proof of quadratic reciprocity, maybe somehow. Yeah, wait, there's something here. There's something here. Yeah, so there's some statement about the following thing. What is it? It's like wait, where's the definition of the number field? So basically, if you take the what is this? A quadratic extension, I think. K, you take some like quadratic character chi, and you take q adjoin chi of -1 times the prime q, and then you should have that the zeta function times the L function is the Dedekind function. The Dedekind function of this number field. Right. And then somehow yeah, so then basically what happens, give me a second here. You're too busy living in a castle and frolicking around your giant estate. Increasing interest and want to start algebraic number theory. Please stop you. You need to do representation theory. Well, this is proving to you that you can do both. L function is basically a universal Euler product, valued invariant of an arithmetic object. Any functorial multiplicative invariant built from its Frobenius action factors uniquely through it. I'm not quite sure I understand what you mean there. Is there any way to begin algebraic number theory without needing a PhD in complex analysis? Yes, just go read Marcus. But eventually you will need complex analysis. You won't need a PhD in complex analysis, but you will need, a PhD level course in complex analysis 1 eventually. Dalawat's article, Splitting Prime, is really fantastic. Oh, okay. Let's go open that. Thank you, Arad. Yeah, so let's see. So I've also got this claim here. So in this setup, if we take, in this setup, it turns out that the Dedekind zeta function becomes, this is over the primes that split, becomes 1 minus ps squared times the primes that are, the product over the primes that are inert of 1 minus p2s inverse times the primes that are ramified of 1 minus PS inverse. And then basically we get the following that so P is ramified if and only if chi P is 0 and P divides Q. P splits if and only if chi P is 1 and it's inert if chi P is minus 1. And then somehow this should correspond to the yeah, this should correspond. So somehow when you unpack these definitions and compare coefficients, you get the implication that the Legendre symbol is equal to this. I guess that's the moral of the story. I mean, I guess that's how quadratic reciprocity falls out of this thing. Something like this. If you can get Cauchy's theorem and know what a meromorphic function is, you should be fine. Yeah. What does a PhD level course in complex analysis cover? Riemann surfaces. I mean, not even necessarily. Like my complex. What was in my complex 2 course? In my master's, I took a course called Complex Analysis 2. And really it covered, and actually you don't even need a lot of that stuff to do this, of what's in that book. It covered what? It covered conformal maps, and Dirichlet boundary problem, which is like differential equations. That was basically it. I mean, these were the main themes of the course, but then, you dive into stuff about function spaces, and it ended up being a lot of like functional analysis and stuff to solve these problems. You wonder if you can get a statement from Langlands through this to use in cryptography. We do use reciprocity laws in cryptography. Yeah, I mean, I know that there's something about applications of elliptic curves, and, well, okay, of course there's elliptic curves in cryptography, but then you can also, because of, like, modular stuff, you can also, like, I know, like, there's some book that's called, like, modular forms and elliptic curves in cryptography. You're damn right I preserve angles, Leo. You're damn right about that. Yeah. Okay. We now study the behavior of an Artin L series at a given point in the complex plane. Beautiful interplay of character theory, finite groups, and Artin L function formalism, from which many important deductions, such as the Armada-Brauer theorem, can be made. Most important of these inductions seems to be the relationship between the zeros of the Dedekind zeta function and Artin L series. So given a point in the plane, we want to study the behavior of Artin L functions at S naught. So suppose we have all of this, and we define a function to be the sum over all the characters. Whoa. And n is the order of the L function there. Damn, okay. If you apply Langlands to cryptography, you're quitting math. I mean, it's basically already happened in some sense. In some sense. This Ant textbook is going to take 10 years to load. Wait, which textbook? Yeah. But I think I should go soon. I think I should go soon. So maybe we'll come back to this document tomorrow. Maybe we will come back to this document tomorrow. But now we know what the ends are. They were eventually explained to us right here. So, thank you all for joining me, and I'll see all of you tomorrow. What does the radius and interval of convergence of a power series mean conceptually? It gives you the largest domain, so you know that power series don't converge everywhere, right? Like, this function is defined everywhere where x is not equal to 1, but its power series only converges when the absolute value of x is less than 1, right? So the radius of convergence says, okay, so say we're at the point like x equals 1/2, right? And you might ask, well, what is say we're at the point x equals 0, and in some neighborhood that this power series converges to this function. And you might want to ask, well, how do you know what's the largest I can spread out in either direction from this point x equals 0 so that my series converges? And the answer is 1. So the radius tells you the largest you can extend it. But if we had chosen our base point to be x equals 1/2, you can see that then our radius of convergence would only be 1/2. Now, of course, you could extend out more this way, but you're talking about the radius. So you're talking about the largest uniform distance about which you can guarantee convergence. I was about to leave, but then people started saying interesting things. The applied cryptography, choosing elliptic curves to do algorithms is pretty interesting. Like, you choose that for Bitcoin's curve? Really? For Bitcoin's curve? Huh. The Bitcoin curve is that specific elliptic curve? That's crazy. And you have to worry about the order of elliptic curves, quadratic twists, because some attacks can swap out curves. Huh. Yeah, I mean, I don't know about like direct application to Langlands, and I don't even know, but I know for example there's a book about modular forms and elliptic curves in cryptography, and so certainly you're using some sort of modularity results there, but I don't really know. You choose small numbers because if you choose big numbers, people think you know something about the curve and have a secret attack. Interesting. Yeah. Okay, I'm leaving for real now. Thank you all, and keep